All right, so in this video, we're going to do some stoichiometry calculations. So we're going to do what's called mole-mole and mass-mass stoichiometry calculations. Okay, and I know from some of my previous videos that I tend to talk a little slow, so I'm going to do my best to try and pick up the pace a little bit. So hopefully this will go a little faster as you're watching this video. So we're going to jump right in. So we're going to start with mole-mole conversions. So the sample problem here says how many moles of NaCl results from the complete reaction of 3.4 moles of Cl2. Assume that there is more than enough sodium. So, excuse me. The first step that we're going to do is we're going to write out the balanced equation. Now remember, stoichiometry is kind of like cooking where we need to have a recipe. And the recipe, it turns out in chemistry, is that balanced equation. So I'm going to write the balanced equation here. It says solid sodium reacts with chlorine gas to produce sodium chloride. So remember, sodium is +1, chlorine is -1. So I have to remember how to put those together. I also have to remember that chlorine gas is diatomic, so it's part of Brinkelhoff. It gets a 2. And sodium is by itself. Now I'm going to change the color of the balancing because I want to make it a little more visual when we get to the ratio part. So I'm going to put a 2 right here, and I'm going to put a 2 right here. And just remember that even though we don't put a 1 there, this is kind of an understood 1. I'm going to write it in just for the sake of this, but generally we don't write that in. Okay, so step 1, check, write the balanced equation. Step 2, I'm going to determine what is given and what the problem is asking for. So given, that's usually pretty easy because it's the only number in the problem. So that must be what I'm going to start with. So I'm starting with 3.4 moles of chlorine gas, and I want to know how many moles of sodium chloride will that make. So I'm trying to find moles of sodium chloride. Okay, notice I'm not like reading the whole entire question. I'm just going straight to here's the number, that's what I'm starting with. How many moles, that's what I want to get to. And I cut out all the other stuff that's part of the equation. All right, so step 2, determine what is given and what the problem is asking for. So now the last step is that we're just going to use some dimensional analysis. I'm going to slide this up a little bit so we can see this, but we're always going to start with what is given, moles of chlorine, and then I want to get to moles of sodium chloride. Now, dimensional analysis. I know that moles of chlorine has to go on the bottom because I have to cancel that out. What do I want to get to? Moles of sodium chloride. Okay, now I need some sort of mole ratio. Now here is all of stoichiometry right here. Where am I going to find this mole ratio? Well, it turns out that the mole ratio will always come from the coefficients in the balanced equation. That is my mole ratio. So this recipe, so to speak, or balanced equation, is telling me that 2 moles of sodium mixed with 1 mole of chlorine gas will produce 2 moles of sodium chloride. So that is my mole ratio. So I just write the coefficients in here. So the coefficient of 1, because it says 1 chlorine, and then sodium chloride, the coefficient of 2, so that's 2 moles. And that is stoichiometry in a nutshell. Just using the balanced equation as a ratio, as a mole ratio, as a recipe. So 3.4 times 2, so this, I don't even really need a calculator for this. I get 6.8 moles of sodium chloride. Okay, and what I should also do is I should cancel out my moles of chlorine. All right, so that's sample problem number 1. Sample problem number 2, I'm going to do the same thing. I have to start with a balanced equation because that is step 1. So step 1, write the balanced equation. It says Henry Cavendish found that when you combust hydrogen gas and oxygen gas, the only product that you will get is water. So you can actually make water if you have hydrogen and oxygen laying around and you combine them together. you can actually make water. Now, again, I'm going to balance the equation, but I'm going to use a different color just to show what this mole ratio looks like. So there's a 2 there, there's a 2 there, and again, there's an understood 1 in front of the oxygen. Okay, so step 1, get the balanced equation, check. Step 2, determine what is given and what I want to find. Given, there's only one number in the problem, so that must be where I am starting. That is my given. Moles of oxygen. Okay, now, without even reading any other part of the problem, I can set this up and I can actually put moles of O2 on the bottom because I know I need to cancel that out. Now I just need to figure out what is it asking me to find. How many moles of hydrogen? So that is what I'm trying to get to. So I'm going to put moles of hydrogen on the top. And again, I need some sort of mole ratio. Where's that going to come from? It's going to come from the recipe or the balanced chemical equation. So there is an understood 1 right there. So 1 mole of O2 is going to require 2 moles of H2. So that is my ratio. Once again, I'm going to cancel out moles of oxygen. Again, I'm going to do 4.13 times 2. That gives me 8.26 moles of hydrogen. So that's how much hydrogen I need to react with 4.13 moles of oxygen. It makes sense because I need 2 times the amount of hydrogen than I do oxygen in order for this reaction to take place, which it is. So that makes sense. I could also calculate how much water I'm going to make, but it didn't ask me to do that. All right, so that's mole calculations. Now, something that's a little more practical is mass calculations, because a balanced chemical equation, those ratios are in moles. So it's moles of reactant to moles of product. But if I go into a lab, I can't weigh something out in moles. I can't say like, hey, go give me 12 moles of Cheez-Its. I don't have anything that weigh that can measure that. But we do have scales that weigh in grams, so that's much more practical. If I say, well, go weigh out 16 grams of Cheez-Its, I can go do that pretty quickly. So grams is a much more practical unit to work with than the moles. Now we're going to use this as our sort of like our concept map. So for all you visual people, this is going to be for you. So what this is kind of showing us, here's how we do any of these mass conversions. We take the mass of whatever A is, whatever's given, and the first step is we're going to convert it to moles. Well, I know how to do that. I know how to do mass to moles. I just find the molar mass. Okay. Now the second step is I'm going to take the moles of given and I'm going to convert it to moles of whatever they're asking me to find. That's our mole ratio. Our mole to mole ratio, remember, comes from the balanced equation. It comes from the coefficients in a balanced equation. Once I get moles of what I'm trying to find, I can easily convert that back to grams just using the periodic table. So conceptually, every single problem will look exactly the same. It will be periodic table conversion, mole ratio off the balanced equation, and then back to the periodic table. So that's the SparkNotes version of this concept map. All right, so here we go. How many grams of water are produced from the reaction of 84.5 grams of C8H18, that's octane, with an excess of oxygen gas? So step 1 is still to just write the balanced equation. So I'm taking octane and I am reacting that with oxygen, because I know that a combustion reaction has to have oxygen in it. And it tells me that this is going to make CO2, and I'm also going to be producing some H2O. Okay? Again, I'm going to use a different color for the coefficients. So this turns out to be a 2, just because I have to double it because I get an odd number of oxygens. So that means this is going to be 16, this is going to be 18, and then when I count the oxygen, 16 times 2 is 32, plus 18, that's 50. So I'm going to come back over here and I'm going to put a 25 right here. So now my mole ratio says 2 moles of octane 25 moles of oxygen. If I mix those two together, I will make 16 moles of CO2 and 18 moles of water. That's my recipe. Okay, so step 1, check. Step 2, determine what is given and what I want to find. So if I go back to the problem, how many grams of water? That's what I want to find. I want to find grams of water. Okay, and so again, the only number in the problem that's given is right here. That must be what is given, which means that's where I'm going to start. C8H18. Okay, so now I'm just going to use my dimensional analysis and my balanced equation. So, oops, I forgot to change the color. So, if I go back to 84.5 grams of octane, so that's my given, again, before I do anything, I'm going to set this up, and I already know grams of octane has to go on the bottom in order to cancel it out. I also know from my concept map that I'm going to take the mass of the known, and I'm going to convert it to moles. So I know that 1 mole of octane equals that number right off the periodic table. And if let's see, I have it right here. Just for the sake of time, I'm going to add up 8 carbons and 18 hydrogens, and I get 114.26. Okay, so I'm going to cancel out grams of octane. I'm going to cancel grams of octane. Now I'm at moles of octane. Again, I know that has to go on the bottom of the next step because I know I need to cancel that out. Now, according to my concept map, I just converted grams to moles. So now I'm going to go moles of my given to moles of my unknown. And I'm going to do that by using the balanced equation. I'm going to use my mole ratio. So let's see. So that means I'm going to go to moles of my whatever I want to try and find, which is water. I'm going to go back up to the balanced equation. Okay, so the coefficient in front of the octane is 2. So I know that this is going to be a 2. And then the coefficient in front of the water is 18. So I know the mole ratio is 18 to 2. You don't have to do this, but if you want to do this, you can reduce this down to 9 and 1 if you want to. Sometimes it makes the math a little easier. But you don't have to do that. You can keep the 18 and the 2. Okay, so now I'm going to cancel out moles of octane, moles of octane. Now I'm at moles of water. I know I don't want that, so I know I'm going to put that on the bottom. And I'm trying to get to grams of water, so I'm going to put grams of water on the top. And now I know, once again, 1 mole of anything equals the molar mass off the periodic table. So let's see. Oxygen 16, hydrogen's 1.01. So this is going to be 18.02. Okay, and then I'm going to cancel out my moles of water, moles of water. So now I have grams of water, which is what we wanted to find. So now I'm going to multiply everything on the top, divide by everything on the bottom, and what we get is like 119.9 or something like that. The only way to make this have 3 significant figures, because that's what my number that I'm starting with has 3, is to do something weird and to put a decimal point after that 120, because that 0 is not significant without a decimal point. But now that it has 1, now it's significant. And if I put an extra 0 after it, now it has 4 sig figs, but I only want 3. The only other way would be to put it in scientific notation. So 1.20 times 10 to the second. And then we need a unit, grams, and we need a substance, which is water. So all of that gets put together into our equation. Okay? This is what's called a theoretical yield, by the way. And it just means, in theory, here's how much I should make of water. Okay? So there's one more. It would be great if you guys that are watching this pause the video and try this on your own. In class, I had everyone just do it on their own, and then I helped out along the way. So I think it's really helpful if you can try and do it on your own first, and then you can sort of watch to see if you need to. All right, so I'm going to go ahead and just do this next one. So it says that aluminum chloride is produced when aluminum, so it says aluminum reacts with hydrochloric acid, HCl, to produce aluminum chloride. So just don't forget, aluminum, the charge is +3, chlorine is -1, so this should be AlCl3, and hydrogen gas, H2, because it's part of Brinkelhoff. Okay, if we balance these, there's a 3, so I know, and I'm going to change the color once again. So I know this is going to be a 2, so that's 6 chlorines, so I know that's going to get a 6. 6 hydrogens, which means we need 3 of these, 2 aluminums, that's a 2. So there is our recipe or our balanced equation. Okay, so that's step 1. Step 2, figure out what I'm starting with, which is 18 grams of hydrochloric acid. So I'm going to start with 18 grams of HCl. Okay, and again, I know grams of HCl has to go on the bottom because I want to cancel it out. I also know that I'm going to convert this to moles first. So moles of HCl. Now if I go to the periodic table, chlorine's 35.45, hydrogen is 1.01, so that gets us 36.46 grams of HCl, right off the periodic table. Okay, so grams of HCl cancels. Now I'm at moles of HCl. I don't want that, so I know I'm going to put moles of HCl on the bottom. I also know that this is going to be a mole ratio, so I'm going to convert this to moles of whatever I want to find. How many grams of aluminum chloride? So that's what I'm trying to find. So aluminum chloride. Okay, and now I need the mole ratio right off the balanced equation. So in front of the aluminum chloride there is a 2, and in front of the HCl there is a 6. Okay, once again, I can reduce this if I want to. I can do 1/3 if I just want to reduce it. Sometimes that makes the math easier. Sometimes it doesn't really matter. Okay, so now I'm going to cancel out moles of HCl, cancel moles of HCl. I have moles of aluminum chloride, which I don't want, so I'm going to get rid of that as well because I want grams. I want something that's more usable for me, that I can actually go on a scale and weigh out. So I'm going to do 1 mole equals the molar mass right off the periodic table. Just for the sake of time, I already added up aluminum and 3 chlorines, and I got 133.33. Okay, now when you do this correctly and you have the correct number of significant figures, you should get 22 grams of aluminum chloride. I hope that was helpful. So for homework, what you guys are going to do is on the next page, you're going to do the 2 mole-mole calculations, and then you're going to do the 2 mass-mass calculations. And I did leave the answer in the bottom there, so you can check your work as you're going through it. But you do need to show all your work, the balanced equation, and all the dimensional analysis. Hope that was helpful.